name is Dan Hebert, and today we will be discussing enabling high fidelity insights with improved movement data quality. So thanks so much for joining us today. Like I said, my name is Dan Hebert. I'm a data science manager here at Foursquare. I've been here for about 5.5 years, leading a team of 9 data scientists and analysts who focus on analytics use cases for movement data, as well as a team that focuses on quality of that movement data. For those of you who might not be familiar, Foursquare is the leading location technology platform. We are in the business of understanding movement and places, and we use technology to, one, understand where things are in the physical world, meaning where brick and mortar store locations, event venues, restaurants, retail locations, etc., are located in the physical world. And two, how people move through that physical world and move between those points of interest. So our tech stack helps businesses use location to guide that decision making and unlock revenue opportunities off of that data. Today I'll be discussing several key challenges that we face in movement data and outline some innovative approaches we employ to tackle those issues. So first, I'll give a quick introduction of Foursquare itself and why quality matters for movement data. We'll then discuss methodologies for collecting movement data and why using the right technology is critical when it comes to amplifying the quality of movement data. We'll touch on the trade-offs between quality and scale. Obviously, quality is a great thing, but if you don't have scale to support the insights use cases for that data, then that can be problematic itself. And we'll also discuss the necessity to build pipelines that are flexible enough to find that sweet spot between quality and scale for different applications. Next, we will talk about driving value in our products by addressing major issues of demographic skew and bias and source panel fluctuations. And then finally, we'll end with a high-level breakdown of different analytics use cases for our data. Of course, at the very end, we'll leave plenty of time for Q&A. First, let's just go into a little bit of background on Foursquare. You might already know Foursquare as an individual app, a user app, a consumer app. We're proud of those app origins, but of course, over the last 13 years or so, we've since evolved as a business, and we've now become a leading location technology platform beyond just the apps that we power today. So we saw an opportunity for other businesses to benefit from our unique technology and data, and that's why we decided to, really think bigger about our play in this space. Today, we're trusted by some of the biggest names in tech, including Uber, Snap, and Twitter. Foursquare's tech stack. So this is kind of going into some of the details of the data that we source and the different downstream applications of it. At Foursquare, we gain scale by taking movement data from multiple pathways into our core proprietary technology, which then powers all of our data tools and software downstream. We make our data accessible everywhere our customers are in order to derive value for a variety of use cases. So here in this visual, we're indicating the parallel ingestion from quite distinct sources. First party is our owned and operated apps. Second party, indicated by the 2P there, is data sourced from partners that we work with that leverage our SDK. So those are partners that have apps of their own that benefit from the location intelligence that we provide through our SDK. And then third party, 3P, originates from external trusted data providers that we work with. Another takeaway here is that there are a diverse array of customers and different use cases for this data. I won't go into too much depth here, but of course, we can come back to get back to that at the end of the presentation. So at Foursquare, we know that where matters. The location is constantly changing, with businesses opening and closing daily, particularly given today's macroeconomic conditions. We're emerging from a pandemic. There's dramatic shifts in consumer retail behavior and foot traffic, the potential for a looming recession. So the result is really unprecedented patterns of human movement that we really haven't seen before. And so clearly business isn't as usual over the last couple of years. Distinguishing a visitor from a passerby is difficult, particularly with signal interference in dense urban environments and also in busy indoor environments. Not to mention nuanced cases like drive-through and buy online, pick up in store scenarios that are becoming more and more prevalent in industries make fundamentally change the type of movement data and the patterns that we see in movement data. When you get location wrong, you risk losing consumers' trust, delivering suboptimal experiences and irrelevant information. It's really important to get location right for any of those downstream use cases. And so that's why the quality of movement data is so important. At Foursquare, the value in our data products comes from translating raw data into meaningful information about places and the movement between those places. So as a result of over 13 years of unique data collection from Foursquare's owned and operated technology and mobile phones, we've created a map of the world not based on coordinates, but rather on actual locations. And I'll get into the distinction we're drawing there. We collect and leverage an enormous and diversely sourced movement data set, about hundreds of billions of GPS records that we've captured over the years to unlock an unrivaled understanding of the device eye view of the world, accurately capturing movement and visits. And what I mean by device eye view of the world is thinking of the world in terms of what your device sees, all the different signals your device collects, beyond just GPS coordinates. So things like barometric data, things like cell tower strength, Wi-Fi routers available to your phone, accelerometer data. So thinking about the world in terms of the way your device sees it. Today, I'll talk you through some of the innovation we introduced to ensure data quality, things you may not be aware of as an end user, because we aim to ensure that you really never have to worry about these things. We'll touch on three aspects of this, three pillars of data quality. Filtering of noise and synthetic defects in source data, and reconstructing semantically meaningful device journeys source by source. We'll talk about the challenge of harmonizing potentially duplicative and or conflicting data from multiple sources, all the way from first-party apps to second-party to third-party. And we'll lastly talk about the need to stabilize and debias outputs in our data products when the upstream sources have their own intrinsic skew and bias and source volume fluctuations over time. So let's move on to sketch out some of the requirements for detecting movement. So what technology is being used at Foursquare today? First, how do we get movement right? Well, first, we do rely heavily on GPS data to reconstruct daily diaries of mobile devices. What I mean by a daily diary is a full sequence that is semantically meaningful of a device's behavior and movement through the real world on a given day. As I mentioned before, our movement pipelines might absorb 100 billion pings. By pings, I mean coordinates and timestamps for each individual mobile device. That is 100 billion GPS records per calendar day of observation. However, there exists inaccuracy in GPS signals. This can happen because of what we call urban canyons of interference, weak indoor signals, other noisy sources, And this might indicate that maybe a mobile device user is half a block or more away from their actual location. That's definitely a problem. In dense urban environments, this can mean, the difference between a person visiting a taco joint versus maybe they actually visited the clothing boutique down the street, or maybe the data GPS is saying that they're visiting a bank and really they're visiting the shoe store down the block. So how can you solve for this and ensure there is truly a visit taking place and that it's registered as a visit to the right place? First is the temporal element. So how do our algorithms differentiate between visitors and someone just passing by? We do this using our proprietary multi-sensor technology for movement understanding. This can accurately detect and segment different types of motion and at scale, solving the question of whether the device is at rest or in motion, whether the motion is pedestrian or vehicular. So this algorithm allows us to decouple those types of motions. We also use inputs of speed, distance, direction, and dwell time, and even the shape of a person's ping trail, meaning the actual shape of, if you were to connect ping to ping to ping over an entire day of a person's behavior, we use the shape of that trail to build semantically meaningful daily diaries of the device owner. Beyond a motion primitive, the next layer of understanding comes with asking, okay, so the person stopped here, but how do we know whether they stopped at venue A and not venue B? So at Foursquare, we use, to solve this problem, we use what we call snap to place. We've built our own proprietary database of POI using place shapes, collecting signals from visiting devices to build a picture of the place structurally in terms of movement of devices in and out and around that place. Context clues like time of day and venue popularity provide an additional layer of insight to optimize our model predictions. A real-time feedback system confirms and continuously improves our model accuracy. So we have a variety of sources of ground truth deterministic labeled data that we're sourcing that helps us constantly improve our predictive accuracy. Another important challenge when it comes to movement data is that we need to ensure both quality and scale. So I was alluding to this earlier, the trade-off between the two. Some clients' applications favor quality or precision. Say an analytics application, something that's going to require maybe insights about site selection or insights about foot traffic trending over time. We call this quality or precision importance like more of a depth preference, right? The quality that the client cares about here is depth. Whereas others, perhaps maybe on the marketer side, are looking for reach. They're looking for data volume, scale, audience reach. This I would call breadth. Fortunately, the movement data pipelines we built at Foursquare are flexible and tunable to optimally trade off between breadth and depth, depending on the application. So addressing the challenge of quality at scale, quality and scale, how do we get there? So at Foursquare, we have a unique competitive advantage. For one, enrichment, we gain initial scale by taking movement data from a large variety of different sources, diverse sources of data. We have a process of data fusion and reconciliation from these different sources. So in effect, the whole is greater than the sum of the parts in that sense. We're able to compare the storylines that different sources are telling about the same user. Sometimes one provider can fill in the knowledge gaps presented from another data provider, another source, meaning there might be actual gaps in those daily diaries of movement behavior from one provider, but those gaps are filled in by another. In extreme cases, one provider may contradict the location of the user when all other sources agree amongst themselves about that location. And we can use a voting system in those cases to reject that conflicting data. A second competitive advantage is provided by our consumer-facing apps, such as Swarm, Foursquare City Guide, and Rewards. The unique user feedback allows us to train and fine-tune our models, providing us with check-in ground truth data and confirmed ground truth of past visits that the user has made. I should say that all users, of course, in those scenarios provide opt-in consent. And because we present the utility to our customers in a transparent way for sharing their location, our opt-in rates are usually higher than industry standards. There's usually some meaningful value proposition that our users get in exchange for opting into to that location tracking or opting into providing us ground truth. We then use this first-party data and data from our SDK partners, that's 1P and 2P data, to further enrich and challenge and harmonize the data that we source from external providers, third-party, basically. Now in this and the following few slides, I'd like to give some flavor of how our movement engine works in the back end. So that this is not so much about injecting, fancy cutting-edge ML algorithms. I find that it leads to more effective solutions if we just take a step back to first frame the problem correctly and architect the solution in the right sort of modular way. Bringing all of this diverse data, these hundreds of billions of pings into our pipelines presents many challenges for data quality amplification. So to start with, we set up blacklists for both locations and devices that will result in Foursquare not using the data. We also set up filters to remove bots and other fraudulent data that's sourced from third-party providers. It is common, it is a prevalent thing to see, and it's something that we take into account with filtering in our pipelines. On top of the remaining data, here are some highlights of our processes for reconstructing semantically meaningful user journeys. So for one, we've built innovative systems around data source deaggregation and eventual reconciliation. So in terms of architecture, we're running parallel independent pipelines for each data source, which helps us handle any panel instability that's sort of intra-provider. And then within this architecture, provider-specific algorithms are tuned to unlock provider-specific quality monitoring and noise filtering, subsequent testing of inter-provider consistency, deduplication, and eventual harmonization into a single fused device timeline. And then secondly, moving can be more confidently identified than stops from raw pings, and this allows more flexible stop detection beyond simply simple density or clustering type approaches. So richer geospatial understanding is made possible as movement and stops are kind of two sides of the same coin in that sense. A third highlight is we are training on our own app feedback. I alluded to this earlier. We were able to leverage first-party user check-ins to validate our movement and visit prediction algorithms and perform data conflict resolution with third-party data. Another key component in getting to high-fidelity data products is that we have aggressive and precise noise filtering for data quality in the upper funnel. And then finally, privacy controls, of course, are central to any improvements that we make in R&D at Foursquare. And this carries into our dev cycle. Data science team works very closely in collaboration with Foursquare product, legal, and privacy teams in any new products that we build to make sure that it's all privacy compliant and that we're thinking ahead to the growing importance of privacy in this space. So let's look at the raw data itself for a second. So something is as you can see from this, evidently raw data. And what I'm referring to there are these sort of, if you think of each of these points here on this map as a ping, a single timestamp and device um, at a location at a given point in time, you can see that there's these sort of grid circles that are appearing, sort of higher density circle of pings in certain areas. So everyone in the industry is familiar with this kind of mysterious, ubiquitous crop circles, we call them, that started appearing in GPS data as of last year. There exist issues like these that are easy to recognize visually, but a challenge when it comes to removing them systematically at scale. So quality amplification begins at the ping level. When we project the classification results on a Foursquare Studio map, the output of the movement understanding pipeline paints a beautifully segmented picture of stops. So in this visual here, when it slides over past the yellow, you can see kind of how we're segmenting those various pings. So in the green points there, you can see tiny green points across that blue map. Those are the actual stops. The movement segments there are colored in blue, which are, as you can see, are kind of nicely overlaid with real streets. And defects, in particular, the red crop circles we just discussed, those are painted in red. And so we're painting sort of this three-color picture algorithmically segmenting those pings and classifying them as stops, movements, or noise. Once identified, this red ping noise is simple to filter out, allowing us to build more confidently on the remaining ping data. The semantically meaningful stories for the users moving through the physical world are thus easier to discern once you've segmented those points out. So here you're looking at just 1,000 users in Los Angeles during a particular week of 2022. This is kind of what I call, maps without maps. And what I mean by that is that the blue colored movement data itself is, as you can see, kind of tracing the roads and street networks perfectly. And that's just using our ping sequences without any reference to maps. The map itself is literally just very, very thin gray lines for the stores, or for the streets rather. And then you can see on the left there the ocean itself. So all other color coding here is just strictly from the ping data that we've sourced and segmented. So let me walk you through some of the components of what we built for this movement engine. As a simple example of one input to understanding and classifying movement is what we call the vector scalar distance ratio, VSDR, which is a trail shape metric. So here there are two ping trails of 12 pings for a single device, or you can think of that device as a user. By introducing a threshold on this metric, we can map from the trail shape to a classification of in motion or at rest. So you can see here in one trail, we have a relatively low ratio, meaning the kind of pings are all kind of clustered together in sequence. And then we have another trail here where the pings are there's much more spread between them, yielding a higher ratio. Think of a bowl of spaghetti, pull out the spaghetti, there's going to be longer strands. And in the bowl itself, they're all sort of kind of clumped together, right? And that's the distinction we're drawing here between, in motion and at rest. So this metric is surprisingly robust against noise, yet still effectively identifies different motion types. So, for example, a device moving in a car or on the highway, or someone walking slowly down the street with their shopping bags. There's clearly a difference there in motion types. Both of those examples, device moving in a car on a highway or someone walking down the street, can be identified as moving. Simply put, those two devices are in motion. If we instead segment motion types on device speed, We discovered that the results in this case turn out to be much less interpretable, so we stick just with sort of classifying both as movement. The algorithmic process of raw data imbues it with geospatial intelligence moving up through the data pyramid, converting it into actionable information and value to clients. So here I want to give a high-level overview of the sequence of pipeline steps, of which this is VSDR, the vector scalar distance ratio metric from the last slide. That's one component only of this process. So the pipeline of getting to semantically meaningful user journeys is one of hierarchical harmonization from individual pings to stop and moving segments, and then from stop and moving segments onto the actual device timeline generation. So the first step is the removal of the noise and synthetic data itself, for instance, the crop circles we discussed. Then follows a ping level classification that tags pings as moving or at rest using inputs such as the VSDR, or the sort of spaghetti shape metric we talked about. And next, pings are bracketed into moving and stationary segments with some tolerance for mismatch between ping type and parent segment class. You can see maybe one ping there in the stop class that might actually be in moving, and vice versa. So there's a tolerance there of kind of the noise that we accept. Next, the pings within a segment are harmonized and or homogenized. And then from the sequences of moving and stop segments, a complete user timeline is created throughout the day. And note this is for data for a particular source provider. So here we're talking about one provider. This is the sequence that we're seeing for a device from that data source specifically. But of course, we're getting multiple providers sending us data. So here we see now a sequence from provider B, which is showing four stop segments and 5 moving segments. So the final stage is harmonization across those providers, which involves the reconciliation of multiple timelines, one created from each third-party source for that device for that day. These multiple timelines undergo a proprietary data fusion process into merging them into a single amalgamated timeline for that user or device. Here we only show 2 providers, but typically for any device, there might be 10 or more timelines that we're actually fusing. I like to think of these timelines like sort of DNA sequences. So here we have discussed only 2 segment types, moving or stops. The next level of complexity means breaking stationary segments into home visits or, say, out of home visits. And maybe for movement, we can segment further into pedestrian or vehicular movement. So now there are at least 4 components, these temporal DNA sequences. For movement, we have pedestrian, vehicular, and then for stops, we have home and out of home. The goal of making the fused offspring timeline semantically meaningful means answering questions like, where is the owner's home? Did they start and end their day there? And there are challenges with home designation too, of course. Up to 25% of the population doesn't work 9 to 5 hours anymore. So it is not always as simple as asking where did the device spend its time overnight. And of course, are overnight stays considered a home visit? What if you spend the night at a hotel or you're traveling? So that needs to be considered as well. There are plenty of challenges as we build out these models for movement. I realize I'm supplying high-level answers to some of these while raising more sort of questions and issues along the way. Not claiming we have all the answers, but that we have a process in place and that Foursquare is actively engaging and continuously developing new and better approaches to crack that nut. So now that we've given a flavor of how we think about movement and the creation of meaningful device timelines, how do you approach your evaluation of location movement data to assess data quality? So putting ourselves in the shoes of a downstream client perspective, someone looking to source this type of data, how do you evaluate the quality of it? What do you use as sort of the foundation for that? Um, so, and another question would be, how do we calibrate the outputs of these movement and visits pipelines to ensure that they are high fidelity and that they are representative of real world human behavior? That's another difficulty when we think about these data sources, is that we talked about inherent bias and inherent skew. So how do we make sort of the outputs of these pipelines look more representative of ground truth? So here are some things you should take into consideration when you're evaluating any movement data. Many businesses will aim to correlate movement data with some form of ground truth or a ground truth proxy. A very common comparison is foot traffic data compared to point of sale data. So transaction volume, dollar revenue, some aggregate form of POS data. And intuitively, it seems like those two things should correlate: foot traffic and point of sale, transaction volume, dollar transactions. However, there isn't always a linear relationship. And one reason for that, for instance, is say we see low correlation, there could be some underlying insight there. For instance, if transactions are increasing and foot traffic is flat, that could signal actually that basket size is increasing, or order size is increasing, but that the number of people actually visiting the venue is staying relatively stable. So we've seen a lot of that coming out of the pandemic, that sometimes traffic is changing. It might be increasing, but not increasing at the rate of maybe transaction volume, and that's just because maybe basket sizes are getting bigger. Or in other industries, it could be the reverse scenario as a result of inflation. So one interesting way to instead evaluate foot traffic data is actually to use it as an input in a model. So so sometimes clients will use foot traffic data maybe for predicting price, predicting demand, or willingness to pay. Using foot traffic data as an input to the model allows you to determine feature importance, with sort of the predictive value of that data. And we think that can sometimes be maybe a more meaningful way to sort of make that assessment on quality in that case. I'll add that it's important in these exercises to keep in mind that you should be looking at relative trends more so than magnitude and volume. So magnitude, volume of visits is a very, there's a lot of different confounders that can affect sort of that scale. And so often a more meaningful way of evaluating stability and sort of the reality of the trends in data is to look at it in a relative sense. And often that means indexing it and comparing maybe across multiple categories, multiple brands, and seeing how that data moves over time relative to those other aggregations. So we of course have a team of data scientists who are location experts, and of course are happy to consult with our clients as they conduct these analyses to make sure that we're designing these evals in a way that supports their use cases. You should also ask, I should add that you should ask about visit frequency per device. So this goes back to the importance of 1P data and always on data. So I mentioned we have, for users that opt into this across our 1P apps, we have always on tracking, which means that the accuracy of those pings and the accuracy of sort of those daily timelines is extremely high. It's basically capturing every single visit the user makes within a day. And so we have a pretty good sense out of that data what the frequency or conversion rate of a device should be to a given set of POI, or points of interest. So obviously, if you see low activity in a panel, meaning you see a device maybe generating one visit or ping in a month, and otherwise they're ephemeral, they're not really, they're constantly churning from the panel, that's a problem. And conversely, if you see high activity, say a user maybe visiting Walmart over 30 times in a given month, that probably suggests that you might be sourcing data about employees or delivery people or vendors. Um, and so, so asking the question of what does that visit frequency look like, and how is the provider accounting for examples of low or high frequency from however they source their data is a really important question, and it's important to get right. So even with this process I just described of reconstructing semantically meaningful daily diaries from raw pings, there remain questions of demographic bias and data volume stabilization. So at Foursquare, panel demographic biases are addressed by a normalization scaling scheme that we call SAG, or state, age, gender. So we use a user's home state, their explicitly provided or predicted age, and then explicitly provided or predicted gender as inputs to a census weighting scheme that we use to address demographic skew in the panel. So we're continually exploring how we can innovate here and improve those models to be even more nuanced. Often demographic details are unknown, in which case we might be able to infer demographics from maybe home locations. We talked about segmenting movement data, and one of those segmentations was getting home location. So it's something we're looking into across to ensure scale, but also quality of demographic information in cases where other demo coverage like age, gender, income is hard to source. So here's a closer look of what I was referring to there as the state, age, gender scheme. So the state, age, gender score itself is calculated simply as the number of people who live in a given state, age, gender cohort according to the US Census. So that's the total population living in that state, age, gender bin, divided by the number of Foursquare panelists living in that state, age, gender bin. So let's use just an explicit case, obviously hypothetical data here. If Foursquare had, say, 500 women aged 20 to 24 living in New York State in its panel, and US Census data shows that for women aged 20 to 24 living in New York, there's actually 50,000 people, then that would mean that each panelist in that cohort would count as 100 people. Right, so you take 50,000 divided by 500, and that's a weight of 100, meaning all of their subsequent visits that each of those users makes will be scaled by a factor of 100. Okay, so final slide here. In summary, I've touched on 3 pillars of Foursquare's approach to data quality. One, we talked about filtering noise and reconstructing semantically meaningful device storylines. 2, we talked about source harmonization, deduplication, and data fusion. And 3, lastly, just then we talked about stabilization and debiasing for derivative data products and use cases downstream. So to finish, we should talk briefly about applications here. So in the most general framing, I think there sort of exists 3 layers of increasing sophistication in how our movement and visit products can be used for analytical applications. So starting with the most basic and commonly encountered, our partners would like to first describe accurately the world of their customers, their trends over time, patterns of movement and visitation, say, how many visits will this coffee shop get in, Berkeley, California? That sort of granular insight. The next level of sophistication is prediction. So understanding predictions of what a user will do in the future, or predict maybe where businesses could or should be located. We call it site selection. And those are based on the features of the surrounding environment crossed with our foot traffic and places data. So you might wonder, am I using prediction correctly? For instance, if I'm interested in site suitability, where should I open my new coffee shop? Should I be trying to predict where coffee shops already exist? There kind of is a subtlety there in what I'm distinguishing between correlation and causation. Perhaps I don't just want a prediction algorithm, It kind of depends on what that question is. Where should I open versus where do coffee shops already exist? And this brings me to the final and most sophisticated application, which is sort of human in the loop decision makers. What they really want to ask is like, what if? That is, they want to leverage our data products and insights to fuel business decisions like, how will my revenue be impacted if I open a new office at this location versus that location? So obviously a very complicated question there of opening a building, growing my business, how will that ultimately impact revenue downstream? So our data is often used as an input to answering complex questions like that. So that's it. I hope you enjoyed this presentation. I think next we'll definitely take some questions, but first I'd really just like to say that we've only really scratched the surface today. Devil's in the details. There's a lot of complexity behind each of these pipelines that we talked about, but just giving sort of a high level lay of the land of sort of how things work over here at Foursquare. Just wanted to call out the many talented data scientists, engineers, analysts at Foursquare who continue to find innovative solutions to really complex geospatial problems in this space. So with that, thank you so much for tuning in, and we'll go on to some Q&A. Thank you.